The rest of you managed to find your way back. So, what I'd like to do for the next couple of lectures, and I should mention ahead of time, next Tuesday, no class. There'll be no class. I'm actually away on a trip. So, just I'll post a note as well. So what I'd like to do in the next few lectures is move on to sort of a topic of more pressing concern when we actually do clustering sort of on large data sets. And I just spent a whole day talking people's ear off about big data, so sadly we're going to have to talk a bit more about that. So what I'd like to do first is, when we looked at all these clustering algorithms, we've seen quite a few of them at this point. What we haven't really paid much attention to is how long they take to run. And in one way that was deliberate. What I wanted to focus on was what these clustering algorithms are doing, what kind of structure they're looking for in the data. And I thought that was the more important aspect of what we were studying in these methods. And I still think that's true. But for what I want to talk about now, I think it's important to look at the computational aspects of these things. How if you actually have to run them, how long will these things take? So this will be a chance to sort of quickly refresh your memory about all the clustering algorithms we've seen. So what I would like to do first is say, let's take all the different methods we've seen, let's look at how long they take to run. And so just to make things easy, we'll say that the number of points is always n. Right? The number of clusters will always be k. And if relevant, and that's not always the case, the dimension of the data will be d. If it's important for your problem. Okay? Alright. So these are the parameters we're going to play with. There are approximation parameters which I won't get into now because for the most part we haven't been talking about particular values. We're just saying, okay, you can approximate this to a constant there. Alright. So, what is the running time of the Kaysen algorithm? There's a good chance to remind yourself as to what a Kaysen algorithm actually is. Does anyone care to volunteer what the Kaysen algorithm is? Or the algorithm we saw for solving the Kaysen problem? The simple. Anyone? Yes, John?
I bet it's like k-means.
Huh?
I bet it's like k-means.
No, that's not.
Not at all.
No, very different. The Kaysen algorithm actually has a nice two approximation. It's a very, you've seen this algorithm. I mean, you know what it is, but it's anyone?
We're going to take point, the first point,
Yes.
and then the next point is the furthest point to the current point.
Yes.
And for the other centers, like choose the point that is the furthest from each center. And
So it's closest distances as far as possible.
yeah.
Okay, good. So we have the algorithm. What is its running time? So again, the algorithm was take a point, take its furthest neighbor, take the furthest neighbor to this side, take the furthest neighbor. Keep doing this till you have k things. What's the running time? Kn. Because at every step, you might have to go through all the data to see which your furthest thing is. And well, is that quite right? So let's say at some point you have k over 2 centers. So at some intermediate stage of the algorithm, I have k over 2 centers, and I have a new point. Right? How long does it take to process this new point?
You don't have any. You want to find it.
Sorry?
You want to find the new center.
We want to find the new center to pick. So we look at all the remaining points and decide which of them is the furthest. Right? So for each of these points, what work you have to do? You have to look at its distance to all the centers, right? Which is k time. Then you have to do this for all the remaining points, which is something like n minus k time. Then you have to do this k times over again. So roughly speaking, as you get far enough into k, you're spending nk time per iteration, per cluster center. And there are k centers. So it's not actually nk, it's nk squared. If you're not being very clever about this.
Can't you just, can you keep the distance to the old center though?
Can you keep the distance to the old center? So what would you do? So you would, the problem is once you add a new center, you have to update all these distances, don't you? So if I now put a new center in,
Yeah, but the scan, that's only a linear scan to update, right?
So tell me your better algorithm. Tell me
So-
how it works.
Okay, assuming that you're going to keep kn space to do this.
Sure, I'm willing to take
Uh,
k in space.
Then what you do is with it, you pick the first center, whatever it is.
Yeah.
And then you get the distance to everything.
Yes.
Right.
That
And
is
then-
linear scan.
Right, and so at this point, and then when you pick the next center, you're going to do the same thing, except that you just update everything, and then you're.
I see.
You just
So-
update it with whichever one is smaller, right?
Right.
And so then after all is said and done, then you just pick the smallest one, or the
Okay,
largest one.
good, that's a good point. So if it's a bit clever, you can get back to the NK one. Okay, good. So we'll. So again, the idea is every time you pick a new center, you update the distance of all the remaining points. You can spend linear time to do this, and then do this again. So at every step you spend linear time, or maybe n plus k time, and then. Okay, good. Let's see. So we looked at. Let me recall this. I think I forgot. So it's been too long. We looked at one algorithm for k-median, if I recall correctly. I don't remember what the algorithm was. Does anyone remember what the k-median algorithm is? Because there's so many different ones that work. So what we said was we actually gave an algorithm for k-median, but I didn't really tell you how long the runtime was going to be. And roughly speaking, what it does is you take a collection of medoids, right? You take a collection of candidate centers, and then you cluster all points around them by using nearest neighbor. And then you pick a pair of a point and a cluster, and you see if swapping them will help. And if it will help, you swap them, and you keep going. Right? And this algorithm is actually quite expensive because basically you have n points and you have, or n minus k points, and you have k centers. At every step, you have to look at a pair of these things so that these many choices to work with. For each of them, you decide if a swap would help you. So you spend linear time for each of these things. And then you do this a certain number of iterations, which is actually not completely clear. So you actually spend at least n squared times the number of iterations you need, which itself is some other polynomial. So I'm going to leave it as some kind of large polynomial, which gives you a good answer, a reasonable approximation, but it's going to be expensive. All right. A similar thing happens with k-means is that I can give you the bound for a single iteration, but it's hard to know exactly how many iterations I need to run. So for k-means, which now will involve d, how long does a single iteration take? In other words, a single iteration of the algorithm involves finding new centers and finding new assignments, points of centers. So how long will this take? So k-means, what do we do? We take a bunch of centers, take a bunch of points, right? So now we assign every point to its nearest cluster center. That's one step. And then you recalculate the centers based on that assignment. Okay? So how long does the first step take? Every point must be reassigned to its nearest cluster center. N times k. What about the second step? Each cluster center must be updated based on the set of points associated with it. All then, right? Because you basically, every cluster center has this particular set of points, you average them all, that takes linear in that set, but the total size is just n. So you basically, each iteration spends nk plus n times some unknown number of iterations. You will often find in papers, people will say, oh yeah, k-means runs in this much time times the number of iterations. So this is not quite right? We don't know what the actual write time is. It could be quite large. T could be, in general, could be very large. Suppose we looked at instead k-means plus plus. Then actually you can put a bound on this. You can say there's some kind of polynomial. But how long does the actual process take? So if you remember how k-means plus plus works, you're saying that, okay, I look at I take my center, set of centers, I pick one center, I sort all the points in increasing distance from the center, and I pick a point a certain probability. So I do some of the k-center computations to create this thing, but I have to do a sampling step. And it's not hard to build a method for sampling once you have the actual values. So we'll say that you can do this in the same amount of time it took to actually construct the set of things.
Actually, initialization is very expensive.
Yeah, it is expensive, but it can. I'm trying to write down what's going to take, right? So you will spend again something like so every iteration you'll spend basically nk, and there's some kind of polynomial here. So t times n times k, which is not too far from this, and then we don't know again what this is. There's some polynomial. So let's say there's some kind of again O of n. Okay. In all this, I'm going to be assuming that k is very small, because if k is k is much small compared to n, so the n is really a dominant term. I'm also ignoring, so another thing I'm doing here is I'm ignoring terms involving b. So in fact, there should be a d here. And this can actually be important, because you actually have to compare long vectors. Okay, so that's so much for the basic sort of set of things that we've looked at. What about something like hack, say single-link hack? How long does that take? Again, you're back in a metric space, you have endpoints, you have k clusters. So what are you doing in single-link hack? You have a bunch of points. And what do you have to do first? You have to find the closest pair, right? So that's going to take some time. Again, in a metric space, you can try to be clever, but in general, it can take a while to find the closest pair. So let's say you spend n squared time to find the closest pair. So you've done that. Now what? You merge them, and you start this all over again. And again, if you're a little bit clever, you can sort of maintain a data structure so that when you want to find the distance from one blob to another blob, you already have this information built up. So, but you still have to spend n squared time per iteration. So if you do this merging step, at every step you reduce the number of clusters. So something like n squared times n minus k is what you're going to end up with, because you have to do n minus k merges to get k clusters. So it's going to be, again, if you're not, I'm not being too careful here, it's going to like O of n cubed. You're not going to do much better than that. Okay. All right, so that's so much for single-link hack. What about if we do something like spectral clustering? Let's look at So of course, spectral clustering has two steps. There's a spectral step and a clustering step. We already know the clustering step involves doing something like k-means, so we won't pay attention to that. Right? And notice that for that case, your dimensionality actually might itself be very small, might be something like k. So let's focus on the spectral part of it. What do you have to do?
Define eigenvectors.
You define eigenvectors. And so you have a matrix, which is going to be some n cross n matrix. And you want to find eigenvectors. Do you ever know off the top of your head how long it takes to find eigenvectors?
It depends on which method you use.
Pick a method.
Okay. Well, if you're doing the whole matrix, then it's n cubed.
Okay. But if you do it by the power method,
If you do it by the power method, I think it's kn squared.
depending on the number of iterations we get.
Yeah. Sorry, much different. Let's say
N squared per
r
vector.
n squared. So
Rn squared per vector.
that sounds right.
Because you have to do this multiplication. Okay. So there are two ways you could compute. So you could say, as John pointed out, you could compute the entire spectrum, the entire SVD of the, the eigenvalues of the matrix, eigenvectors of the matrix, and that'll take n cubed time. So that's one approach. I should also point out this also takes n squared space. I haven't talked about space, but this is an issue, right? You have to actually store this entire matrix. It's very hard to do this.
This is then completely impractical.
Yes. And your point too.
What is really my point?
What is your point?
Like, if I have 10 to the 6 points, I would need 10 to
Okay,
the
but no, I agree. But again, what is your point? So, why are we doing this exercise?
No, I wanna know if you can do it faster. That was my point.
But
There are
if
approximations.
you had come in 5 minutes earlier when the class started, I said the goal here was to understand the running time of the algorithms we discussed in class as a motivation for how to improve the running time.
No.
See, you missed the punchline. That's why it's good to come on time. So this takes n cubed time if you take the entire eigenspectrum, and it takes n squared space. And if you, another way to think about this is you only want to compute a top few eigenvectors or bottom few eigenvectors, depending on how you look at it. And so in that case, you don't need the entire spectrum, you just need a few k of them. And so there's this method called the power method that basically says, essentially if you have a matrix and you have a vector and you keep multiplying it, so you keep, you find ax, a squared x, a cubed x, and keep doing this over and over again, you will eventually converge to an the top eigenvector then you have to subtract it off, and then do this all over again, get it with a new matrix. There's a way to peel off essentially the eigenvectors of the matrix one by one, which is more efficient if you only have a few of them. And each of these will take some number of iterations times n squared time, because that's how long it takes to do multiplication, and then you pay a factor of k for each of them. So still, so one bound would be n cubed, another bound would be something like this. So this is the number of iterations you need. Okay, so that's so much for spectral clustering. Good. What about correlation clustering? So in correlation clustering, again, we had this very simple algorithm that said something like the following. Pick a random point. Remember, we're given a matrix of plus ones and minus ones, or plus w's and minus w's, or as your case may be. And we said, pick a random point, put it in a blob, and bring in all the points that have a plus connection to it. Take everything what's left and start all over again. So this actually, as an algorithm, is fairly straightforward. What you're going to spend is, you're going to pick your point, you're going to scan through the set to find the things that are pluses, right? So you have to scan the row for this element, so that might take linear time to do this. And once you do that, you remove that set, and so you basically get something like, you pay n time, so the running time is t of n, you're going to pay n time just to do this first scan, and you're going to pay some n minus r, where r is the number of points you actually pulled into your cluster. You don't know that ahead of time. So in the worst case, you might just pull in a little bit of stuff ahead of time. Everything else may not be pulled in. So this could, in the worst case, could be something like O n squared. But it could be a lot better. It depends on the. So I think this covers most of the algorithms we've seen. Other things we've seen have been variations, and I'm not going to talk about meta-clustering and other things like that for now. But this is kind of a summary of where things stand if you want to cluster a collection of points. Right? So you pay this, or this, or this, or this, or this, or this. In general, you're either paying some high polynomial in n, or you're paying linear in n per iteration with some large number of iterations. K-sub is probably the only one that you can actually do pretty fast, which is nk. So from the point of view of efficiency, this is probably the best one you have at your disposal. All the other ones are more expensive. And they all involve sort of some polynomial in n. Okay. And that is the motivation for what we want to talk about now, for the next couple of lectures. When you're dealing with large data sets, anything even reasonably large, some polynomial n is no longer good enough. Right? If your data set is large enough, even n log n is not good enough. Even n is not good enough for some reasons. But at the very least, n squared or n cubed is not going to fly if you have even, I don't know, 1,000 points. And the space bounds, if you have, a million points, you can no longer actually run spectral clustering efficiently if you just want to compute the eigenvectors. There's just no space to do this. Right? So this is a theme that you have probably seen in other classes as well, and I've sort of mentioned this in algorithms, that at this point, if you want to make these things work at scale, there are very few options if you want to solve the problem with that. Your options really are to start sacrificing accuracy, start being approximate and so on. And so what we want to look at is different ways you can solve clustering problems with approximations by sacrificing error in some way, but that gives you a much better running time than what you're getting. Okay? So can we do better? And again, this is, while these things are always important, it's always important to know how things work at scale. But I think for clustering, this is particularly important. Because clustering is often an exploratory tool, a theme I keep harping on. Because it's an exploratory tool, it's a tool you're using when you don't know much about the data. And when you don't know much about the data, you don't know what to throw away from the data. You sort of want to keep whatever you have. So you're often clustering a very large data set in the hope of reducing it to something a lot smaller. Maybe you cluster it, you find some interesting clusters, and then you go explore the clusters. And the clusters are much smaller in size. But when you start the clustering process, you have a very big data set. So there may be some problems for which you're never actually running the algorithm on something that's very big. That's not going to happen here. Here you are actually going to use at scale. So it does matter what you do. Okay. All right. So what should we do? How should we go about designing good clustering algorithms that work reasonably well at scale? There are a number of tools that we've developed in our toolkit for doing things approximately. And we will cover a few of them in this class. We may not be able to cover all of them. There are other classes that do a better job, I think, of covering all these things. But one of the most basic ideas, and if any of you have taken a geometry class with me 2 years ago, I think. Did any of you take the geometry class with me 2 years ago? 1, 2, 3, I say. Yeah, so there's this notion that comes up in there called a coset. And a coset is a very simple idea. It says, I have some data set, X, and I want to compute something on it. And let's say best class. What I want to figure out, if there exists, does there exist some set S, which is subset of S, X, such that the cost of the solution on S is more or less, up to some epsilon error, the cost of the solution on X. Of course, this by itself is not useful, except that we want okay. So in other words, what you want to find is a small subset of the input that somehow captures everything you want to know about the input for that problem. In the sense that its solution, if you run your algorithm on this subset, it will give you more or less the same answer as you get from the input. But because its set size is so much smaller, you win. So in particular, right, suppose you had some algorithm whose running time was T of n. And I took a data set for which a core set had size, let's say, S. And let's say it took me a linear time to find this core set. I scan the data, I do something, I find the core set. So our original problem, we'd be spending T of n time to solve it. But the core set, we'd be spending n plus T of S time. Because we spend linear time to find the core set, and we'd run our algorithm on the core set. And we'd know that our solution is close to the original solution. And the game here, of course, is between this and this. That if you can, if your S is very small, then you can get huge benefits from doing this transition. Right? And it's like the kind of a plug-in method, right? I mean, you have some algorithm, instead of plugging in the data, you just plug in the core set for the data. The algorithm doesn't care, it just runs. But then because of properties of the core set that you proved, this whole thing works.
The run time is usually linear.
Depends on the problem. But a lot of times you might do some kind of random sampling, or you might scan the data and do something with it. So you generally, you might have to spend, and you might get lucky, you might be able to do less than that. And just to get a sense of what you would like, for example, suppose you could say that S was some function only of your error term epsilon. Right? Then basically you're getting a term involving n, and you're getting a term involving epsilon. And that's a big win. Because then your error is what controls, the desired error is what controls how long your algorithm takes, not the actual size, up beyond, just reading it. Okay? The fact that core sets even should exist is kind of miraculous. There's no, if someone said, okay, I want this kind of property for a problem, there's no real reason why such a beast should even exist. Right? Why should you believe that a problem admits this kind of small representation that can do this for you? So let's start with a simple example that sort of illustrates what's going on here. And so it's a clustering problem, but a simple version. Let's look at one center, or the MEP. Yes?
Can we find a core set for the core set and express the error as the function of number of cores?
You mean do it over and over again? You could. What will happen? What do you think will happen? Well, what's the catch? There's always a catch here. What do you think the catch would be?
I mean, how does error change with the number of functions?
Right. So the thing is if you make the set smaller and smaller, your error will increase.
That cannot say that how the error function there is may not be proportional.
Well, it depends. It depends on the problem. So in general, if my problem constructs a core set whose size is independent of the input size, then it won't matter. Once you get the new core set, you're not going to get, it's almost fully compressed at that point, right? Because you're not going to get any benefit from that. Right? Suppose I said, oh, there's a core set of size 5. So I compute that core set of size 5. Now if I say, okay, what's the core set of this? Well, it's of size 5. I'm not going to get any benefit because that 5 is linked to how much error I'm willing to pay. So in fact, the better your initial core set is, the less likely it is you're going to do it again and again and again. But you're right that there are ways to combine courses in interesting ways. And I'll talk about that. All right. So let's look at this problem. In the one center MEB, you have a bunch of points, right? And you want to find a minimum enclosing ball. You want to find a single cluster, if you wish, a minimum radius. So it's like just the one center, basically, that encloses all the points. Okay. Now, is it possible? At least this, before we think about anything else, does it even seem reasonable that this might admit a core set? That there might be a few points that could give you the same, whose a minimum closing ball would be the same as a minimum closing ball of this. What do you think?
Sorry, I didn't understand.
I'm just saying, I gave you this problem, the MEB. Conceptually, I've defined what a core set is. Do you think there's any reason to believe a core set might exist for this problem?
What's
And if-
the problem?
Huh?
What's the problem?
Finding the minimum closing ball of a collection of points.
You mean the convex?
The minimum closing ball,
Oh,
the one center.
Yeah, 2 farthest points.
The two farthest points. So, I see. So you're saying there's some point here, and there's some point here. Something like that?
Some point on the ball itself, right? 2 farthest points will lie on the ball.
Suppose there are no points in the ball. It's a bit of a trick question. You're not allowed to answer. You're not allowed to answer.
so I don't even understand the problem.
So the problem is, do you understand the MEB problem?
No. What's the MEB problem?
Minimum closing ball, one center, the one version of K center. Do you understand the K center problem?
We want to cover the set with K centers.
Okay, suppose I put K equal to 1. Then I call the set with one center,
Okay.
right? A minimum radius. That's a ball. So it's also called a minimum closing ball. That's a problem.
So does the center have to contain the point or contain the point?
Either way, I'm flexible. You can, if you want to, then yes. If you don't want to, it doesn't matter. That's in fact, I take that back.
It doesn't matter.
I take that back. Let's assume you're an RD.
Then what's the problem? You just select the center.
You select the center. That's not.
You compute the center, not select.
No. But I want to see if a core set exists. I want to see if there's a set of small size, so that if I took that set and plugged it into my magic algorithm for the one center, I'd get an answer that was close to the true answer. I'm not trying to solve the problem. I want to see if it admits a core set. Yes? Your question or your answer?
So, I mean, I don't know if this is the right answer, but what if you take the convex hull?
Okay, so the one proposal, take the convex hull. So if you take the convex hull, you'll get a whole bunch of points on the boundary, right? And what your claim, John, is that if you looked at only the points in the convex hull, that will suffice. So does the claim make sense? So this claim seems reasonable. Can we say that it's actually correct? That if I took a bunch of points, so by the way, I should check though, how many of you know what a convex hull actually is? You need to put your hands up higher, I can't really see. How many of you know what a convex hull is? Okay, how many don't know what a convex hull is? Come on. Okay. So let me first explain the convex hull. Take a bunch of points in the plane, take a gigantic rubber band, let it go around them, let's snap. You'll get some kind of thing like this. Yeah? That's a convex hull. Take a bunch, one 3 dimensions, take a gigantic rubber sheet, let it go. You get this polyhedron. That's a convex hull. So it's like stuff on the outside. That makes sense? Okay. Now go back to the claim. The claim is that the convex hull is a core set. In that if you just looked at the points on the convex hull and ran your algorithm on those, you would get a same or very close to the same answer as you would get for running on all the points. What do you think? Seems reasonable? Yes? Yes?
Yes, all the points can be convex.
Oh, you're jumping ahead. Hold on. I'm getting, yes, I know it. Oh, you're still wait. So okay, so you can in fact take the, so at least there's a proof of concept that there is some set. If you had a whole bunch of points in here, this is a useful observation. We don't need to know about the points in the interior. They're not going to change the boundary. The only things that affect the boundary are the points in the boundary. And the convex hull is one way to find these points in the boundary. So that's great. And of course, the problem comes in if your data set looks like this. As Samir was pointing out. So if your data set looks like this, you can compute the convex hull of the set. So you compute the convex hull. What is the size of the convex hull? It's the size of the input. The whole point of a core set has to be that it's smaller. If it's going to be the same size input, you've done nothing. You have not saved yourself anything. And you might say, well, in practice this won't happen, and that's true. But if you'd like to give a guarantee that no matter what you do, you'll get a better answer, this is not going to help. Yes?
What if you find a core set for the convex hull?
But how? You said the only algorithm we have right now is to take the convex hull of my set.
I'm just kicking it down the field a little bit.
Yeah, sure. No, but you can actually do this recursive. But the point is that if all you have as a core set construction is to compute the convex hull, once you set is convex, you're stuck. You can do nothing more than that.
What if you take just the 2 points that consist of?
I don't think you mean 2. I don't think you mean 3. I don't think you mean 4. I think you mean something else.
T plus 1.
Thank you. Well, I told you, you're not allowed to answer. So the observation here is that this is all very silly because there is some like very far apart pair of points that's holding things. And that's probably the intuition I've been hearing from. There's some far apart pair of points. Because far apart is not quite what you want in higher dimensions, but in 2 dimensions, it's almost right. It's almost right to say that you can look at the pair of points that are furthest apart, and their diameter, the ball containing them, will be in fact something that closely approximates the true core set. But this is not quite right. So where would they go wrong? There's a very simple example where choosing the 2 farthest points will not give you any reasonable answer. Yes?
Outlier.
Sorry?
If you have outlier,
Can you describe what such a set might look like?
they have point.
I have 2 points far apart. Okay. Yeah.
Take the circle.
Draw a circle.
No, the first circle you.
The
green
circle?
one, Yeah.
This circle.
Yeah.
This very, very pointy circle.
Yeah.
Okay.
And,
All right.
And at a point much far from it.
Like here?
Yeah.
Okay.
Now the center changes, right?
But shouldn't it? If I want to compute a mean closing ball, it has to include that point, right? That's fair. So my set would be this and maybe that, and that would be a correct thing to do. So what's an example?
What you put these 2 points far apart, but then all of the others just almost there are on the other side.
So you have these 2 points, and where are the other points?
Where are these 2 points?
Okay, so let me make a new diagram. So I had my 2 points.
Yes. Okay, and these are, now you put all the other points on the right side of
Here?
this, but just a little bit less than R.
But then this is not the diameter pair. You said take the 2 furthest points. Right? 2
Oh,
points
yeah,
here.
yeah, sorry. Oh, gosh.
So look at this example. It's an equilateral triangle. Okay? Take the two furthest points. It's an equilateral triangle. Take these two. Right. There's a ball containing them. I haven't drawn this quite right, but this is going to be outside. You can. It's not going to change, and you can show that it will be certain distance away. And you can't make this any better. And in fact, it turns out what you need in 2 dimensions is 3 points. One way to think about this is that how many points you need to describe a circle uniquely in 2 dimensions. You know, a circle in 2 dimensions has an x coordinate of center, a y coordinate of center, and a radius, right? There are 3 things. So you need 3 points to describe it. So if I gave you 3 points, they could describe any circle. In particular, they could describe the circle you happen to have. Okay? So there's some 3 points. I have the circle, and I can take 3 points on the boundary. But now this is the problem that I asked before. What if all my points were like this? Then these 3 points are no longer going to. They're not part of the input. I want points in the input. What do I do in this case now? This is my optimal ball, and these 3 points no longer lie on the boundary. They're no longer a part of the input that I want to pick. Can this happen? I'm going to claim to you this cannot happen. Why not? This ball is special. What's special about this ball? It was the minimum enclosing ball. Is this in fact a minimum enclosing ball? Why not? Sharad is shaking his head. Why not?
Can draw into one which which is smaller than.
You can draw the smaller, right?
Okay.
Huh?
Do it again.
Again, I just did it once. Okay, fine.
Till you reach the.
Till when?
So you can't go
Till
any
nothing
further.
outside.
Till nothing is outside. Till you can't go any further. What does that mean?
Until your ball is too small to enclose it,
Yeah.
What would prevent your ball from getting smaller?
if you have a point outside of it.
Yeah.
If you have a point outside of it. So in other words, you can keep making this ball smaller till some point starts pushing in it. And you can show that if you have the minimum closing ball of a set of points in the plane, at the point when it's optimal, there must be, in the general case, 3 points on its boundary. Because if there isn't, you can make the ball smaller. Right? So in a degenerate case, you might have 2 which sort of hold it off, but in general, you might have 3. So for example, let's say I have the ball here. Okay, I have 1 point here and I have 1 point here. Right? And all my other points are kind of here without touching the boundary. Okay? Then you have to visualize this a bit. You can essentially shrink this ball a little bit. It pops out a little bit more here, it shrinks a little bit there. But because there's no point touching the boundary, you have a little bit of room to move that ball in. A little bit. Just enough to show that it's not optimal anymore. And you can keep doing this as long as there's no third point that's preventing it from moving any further. Okay? So the minimum closing ball of set of points in 2 dimensions will touch in general position 3 points. I say general position because there may be some cases where it stops at just 2 points, but at most 3 points. It could have, well, I wouldn't say at the most, but you can even have more if they're all in the boundary. But D plus 1, 3 points are sufficient. And in general, if you have RD, D plus 1 points are sufficient to lock down the ball, just to find the ball. Okay? So our core set procedure would look something like this. So step 1, find a set of size D plus 1 points. Find MEV of S. Report answer. And how do you find those D plus 1 points? Well, it's very easy. Just compute the minimum closing ball and look at the points that are touching the boundary. Wait, what did I just say? You're all nodding. It just says something completely nonsensical. Did you catch it? You're nodding. Did you catch what I said?
Are we doing, we have to do the same thing?
No, it's just he said find the MEB. I mean, it's like,
Yeah.
I said find the MEB
That's
the
the
whole
whole
set.
thing.
Yeah.
So how am I supposed to find this set? I claim this. So all I've shown you is that this core set must exist. But I don't know how to find it. It's no good for me to tell you something exists without being able to find it. Well, in certain logics it's okay, but in our world we actually want to construct the solution. So,
if you're in more than 2 dimensions, this is too expensive.
sorry?
If you're in more than 2 dimensions, this is too expensive.
To
Find the MEB. You need to do the convex hall, right? I mean,
no. Why do I do the convex?
You don't need to do the convex hall to find.
I actually have not given you any algorithm to find this set of deep% points. I just said they exist.
Yeah, I'm asking you, what is the optimal way of finding the MEB of any points in our given space?
Oh, exactly.
Yeah.
It's the running time of the best known algorithm for computing the MEB. Exactly
Is
is
any better the convex hall?
is ta-da, n linear n times e to the square root b.
What?
It's awesome. It's some exponential. This is the best known exact algorithm by Matuszek, Sharir, and Welson. This basically takes a modification of linear programming that works for the MEB and gets you the solution. We don't know of any algorithm that works better than this, but there may be one.
That's E. That's E, constant E.
Yes.
Still exponential.
That's super good.
Okay. I don't know. I feel so intimidated by your hatred of algorithms, of these algorithms, so I felt like I should, at least defend myself here. But if you like this one, I'm happy. I'm happy to.
Are you sure we can do it so fast?
Well, yeah. I think
Exactly?
Huh? Yes. This is a result from 1991 or 2 or 3. One of those 3 years. There was a series of papers that very quickly sort of came to this one. It's a very beautiful result, actually. You basically have to take an LP and you randomly select some of the constraints and then you recurse from that. It's a very beautiful method. There was an earlier paper by, how does this go? There was a paper by Clarkson that gave you d to the d, and then this improved it to e to the square root d. It's kind of nice. So that's the best one we can do for exact case. So we're not playing in the exact world here. That would be hopeless. And by the way, if we actually had to implement this algorithm, we would have to try basically all possible, the dumb algorithm here. We say, okay, let's look at all possible subsets of size d+1, compute the MEB of this subset, and then see which is the best one we get, which actually contains all the input. And then you'd spend basically n to the d+1 time just to do that. It would actually be n to the d+2 because you'd have to check that the result was feasible. But it would be very expensive. Yes?
You could find the convex hull and then check for all the triples.
Or the d subsets. You could, but again, suppose all the points on the convex hull, then you wouldn't save anything. I agree that that's a good heuristic in practice. Okay, let's not worry about everything except the convex hull. But after that, you still may have a lot of points. You might have n over 10 points on your convex hull. Then you still have to pay this into the deal. So what we'd like is something a lot better than this, right? Because remember, we didn't say that the MEB has to be exactly the same. We said it should be close. And we don't care for it to be the exact answer. All we know is that there is some set of size d+1 that gives you the exact answer. Maybe there's a set that's a bit bigger, but gives you an approximate answer. That's good enough for you. Right? And so here's what I'm going to tell you what to do. So I'm going to make a claim, but I'm actually going to prove only a weaker version of it. So this is the claim. And this was kind of a very surprising result when it was first shown, because it's just so bizarre. For any, yes?
It's a randomized operator.
Yes. For any points at P, there exists a set of size 1 over epsilon, actually maybe 2 over epsilon. Okay, C. That's a subset of P, such that the MEB of S, now it's a subset, so its MEB is going to be smaller. Right? So then this is greater than or equal to 1 minus epsilon times, so this is the actual radius, MEB. So it's smaller, but not by much. And the reason this result is so shocking is, first of all, that it's independent of n. But secondly, that's independent of d. It doesn't seem to matter what the dimension of your space is. So you're getting a win on two counts. You're saving the space you need in terms of n and in terms of d. And so this, so yeah. So if you had some exact algorithm for computing the MEP that was something expensive or something, that was hard to do, you could actually do it in n plus that function epsilon, a function of 1 over epsilon. So does this claim make sense? I'm actually not going to prove this particular thing. I'm going to prove a slightly weaker version of it. Because it's a little bit technical to prove this particular thing. But does it all make sense? Okay. So just to give you an idea for why this should be true, I will give you a construction, an explicit construction of how to come up with the set. Because obviously I need to compute the set, so I'm not to say there exists one. So I'll give you a construction for a set of size a little bit worse. It's O of 1 over epsilon squared. So it's the square of the size that you really want. So it's worse than that, but it still again is independent of n. Okay. And I'll only give you a sketch. I won't give you the entire details, but there's a very key lemma there that's kind of very useful here. And the property that you want, that you're going to use, is the following property: that if I give you a set of points, and I compute the minimum closing ball. So there's a minimum closing ball set of points, so there's some points in the boundary. Okay? Then, if I take any plane through the center of this ball, there is always one point. So think of the plane as being directed. So this is kind of the half plane that's looking this way. There's always one point in that plane on the boundary of the circle. In other words, that circle has been kind of extended out. No matter which direction you look at it, it needs to be extended out. So to get a sense of what this might mean, let's look at what would happen if this were not true. If this were not true, you might have the following situation, where you have a bunch of points. So again, I'll draw a circle first, and I'll draw the hyperplane first. And suppose this condition is not true, then for this hyperplane, everything lies on one side of it. Okay? There is no point on the other side. And what this is saying is that, well, if that were to happen, then I should be able to shrink this ball further. Because everything's on one side, there's a way to shrink it down. And that point I'm looking for could be at the boundary here also. It's included there. But it can't be, if it's only on this side, then intuitively there's a sort of less than half the region is where my points, and I can shrink them a little bit. There's a proof that you can. So every half plane must have one point on the other side of it, on the side of it that you're looking at. Okay? And this is a certificate that this actually is optimal. That if this were not optimal, you wouldn't have this property. Or that if you know this property is not optimal. Okay? Yeah? Okay. All right. So the way we're going to do this, the algorithm we're going to use again is quite simple. So the algorithm will look like this. It's going to look a lot like some things we've seen before. We're going to say, pick any point, and its furthest neighbor. Okay? Look at the ball around these 2 points. Okay, so let's call this set S. If the ball around S, okay, scaled up by a 1 plus epsilon factor, okay, the opposite of this, contains P, then stop. Why? If you have a ball that is almost close to containing the whole point set, then if you open it up a little bit, you get everything, and you're done. That's the property you wanted, right? Then this property is true. Because roughly, for small epsilon, 1 over 1 minus epsilon is equal to 1 plus epsilon. Okay, all right. If not, there exists some point P outside B of S times 1 plus epsilon. So there's some point that's far enough away from the ball. Right? So in other words, you look at the points. So you get your initial points, and you look at the ball around them. Right? If all your input points are kind of here, they're inside, maybe they're a little bit outside, then you're done. That's step 2. But if there is some point that, if step 2 is not true, that means there's some point that's sort of reasonably far away. Right? Any point. And then add B to S and repeat. So it's very much like a relaxed version of the K-center problem. Right? You take points, try to find some point that's far away. You're not looking at the point that's furthest away. You're just looking for a point that's far away. Then add that to the set and then keep doing this. The claim is that this process, so every time you do one iteration, you add one more point to your set. So in order to prove this claim, I need to prove this process stops in 1 over epsilon squared steps. When I say stop, I mean it reaches step 2. Okay? And the key observation that makes this whole thing work is the following claim. So let's say that after the ith iteration, the radius of the ball you get is Ri. Okay? So you have R0, and you have R1, you have R2, and so on and so forth. So, like that. Okay? So let's look at what can we say about R0, the radius of the ball we get. What we can say is that since this is the furthest pair, the radius of this ball is at least the diameter of the point set divided by 4. It has to be at least that much. This is by triangle inequality. It's very easy to see. This is the same argument we use in the case. And another point to note is that we will stop if at some point, for some value of k, rk becomes more than delta, right? Because if rk becomes more than delta, well, delta over 2, delta, then you clearly got everything. If the radius of your ball is the same as the diameter of the point set, then you clearly captured everything. There's no question about that. So the main thing we have to figure out is how long is it going to take us to go from this to this? We are increasing the radius at every step by adding more points to it. But maybe the radius is increasing very, very slowly, right? At every step, you just add a little bit more to it, and so you have to add a lot of points to get from delta R4 to delta. And so the crux of the claim, the crux of why this whole argument works, is that Ri plus 1 is always greater than or equal to Ri times 1 plus epsilon squared over 4. The 4 is not an important thing. It's part of the proof, but just think of it as some constant. Actually, it's not even 4. It's 16, in the actual proof, it's 16. So let's say some constant. I don't want to get distracted by that. So what is this saying? This is saying is that the radii are increasing rapidly. How rapidly? Well, it's basically going up by a multiplicative factor at every step. So this is going up by this factor. So let's call this factor alpha. Okay. And let us say that it's going so that we can say that Ri plus 1 is greater than or equal to alpha times Ri. So we know that R0 is greater than or equal to delta over 4. We know that when it stops, Rk will be around delta. So how many steps will it take you to go from here to here? Well, at every step you're multiplying by alpha. So roughly speaking, when alpha to the k is equal to 4, you're done. Because if once alpha k becomes equal to 4, you've gone from delta over 4 to delta. Okay? All right. So when will this happen? Well, this will happen basically when, so k is equal to 4 divided by log alpha. Right? Okay, but what's log alpha? So k is equal to 4 divided by log of 1 plus epsilon squared. And if you remember your basic tricks with logs, the log of 1 plus a very small number is that number by Taylor expansion. So this is roughly for small epsilon. Divided by that. So in other words, as long as we can prove that this is true, that the radii increase rapidly enough, you get a bound of 1 over epsilon squared, or O that 1 over epsilon squared, which is exactly the promise that we made. Okay? And so that's the entire algorithm. So again, as always with these things, the algorithm is very simple. Just keep adding points as long as you need to add a new point, which means that it's, it's sufficiently far away. And the analysis will hopefully tell you that this will stop at some reasonable time. Analysis is not too hard. Again, proof is not terribly relevant right now. But if you're curious, the basic idea is that when you add a new point, one of two things can happen. Either a center moves by a lot or it moves by a little. If your center moves by very little when you add the new point, right, then you can show the new point is actually, that the new radius has to be quite big. Because your center didn't move very much, and this point is very far away. So your new radius has to be very big. Okay? Or the center moves by a lot, because some of this point pulled the center away. Then you have to use this reasoning that I was telling you about earlier to say that, okay, even if the center moves by a lot, the new radius is going to be reasonably large. So there's a two-step proof. Yes?
So I might be jumping the gun a bit here, but so how can you embed this to clustering when you have more than one center? Like how do you resolve the two NUV problems?
There is a very vague sense in which some of the core sets for clustering use this kind of trick. Basically what you do is you find one cluster using this trick, peel it off, and then do it again. And then peel it off, and then do it again, peel it off. You get horrendous bounds from that. So I'm not actually going to talk about those methods. There are other ways of doing courses for clustering. So I'm going to give some intuition for all those things. But yeah, that's one idea for how it's. I mean, the whole point here is to basically give you an actual example of course of construction, somewhat more explicit than just, okay, I promise you this thing exists. So yeah, so the intuition for why that works doesn't quite adapt itself to multiple constructs. Okay, so this is basically our first proof of concept, that you can construct a set of small size that witnesses the property you want of coming in MEB. And in some sense, you can think of this as your summary structure for the data, right? You can now throw away the rest of the data and keep this around. Every time you want to compute enclosing balls, you just need this. And because the set is small, much smaller compared to n, you've got a way. If you want to compute it, you can do all of it. Okay. And so this whole idea of a core set sort of permeates all of what we do with sort of these large data problems, whether it's clustering or other things. That you want to compute some small representative that has all the important information you need, and you can throw away all the rest. Yes?
I was just wondering, can we somehow use Warner diagram to find the core set?
Can you use a Warner diagram to find the core set? Tell me how you do that.
Hypothetically, we have the Warner diagram for the given set.
You have the Warner diagram for the given set. Well, yes and no, but let's pretend you do. There's a problem with that, but okay, let's carry on. So you have the Warner diagram.
Can we use it to efficiently find a core set?
I know, but how? Well, let me ask you this way. Why do you think the Warner diagram will be helpful to you?
In every segment or sector, there are a bunch of points which are kind of a grouping. So we find a representative from each group, which will give us the information about the.
All right. So the idea is, let's look at the Warner diagram and somehow partition the data. But if you build a Warner diagram, every cell has one point in it. So I'm not sure what you mean by grouping. What you could do is take a random sample of the data, build a Warner diagram of that, and now in the Warner diagram of the random sample, you have lots of points inside each cell, because you put back the rest of the points. And now you see a cluster with respect to that. So there are some problems with this, mainly because the Warner diagram of a set of points is exponential in the dimensions. So you don't want to do that. But this idea of taking maybe a sample of the data, using that, is interesting, right? So suppose so maybe a better argument for this would be, let's take a random sample of the data of appropriate size and declare that to be our core set. What could go wrong there if we just took a random sample?
The distribution may not be anything.
Right, so what would be a bad distribution? What would go wrong if you try to build a core set based on sampling? So think of how to beat, think of it as the inverse way. How do you beat the algorithm? What would you do? How would you distract it in the sampling? So what you would do is something like this. You would, so I want to pick up these points, right? Put a whole bunch of stuff in the middle. Your random sample is going to be drawn to the center. It will not be able to shake away. And in fact, let me make a stronger argument. The very fact that a core set exists in some way says that random sampling is not going to find it for you. Why? Because the core set is supposed to be small. Random sampling is very bad at finding small things. It's going to find things that are scattered everywhere. Right? So then sometimes even though there are cases where you use randomized algorithms to find a core set, you can't use random sampling. Because the thing you're looking for is very, very small compared to you. That's the whole point of it. And that's why it's going to be a tough. Now you could say, well, like, if I could somehow group these together, maybe I could be more clever. Which brings us to the next idea. Okay. All right, so any questions about this sort of simple core set construction? All right. Suppose we want to build, yeah, you had a question? Yeah.
What would be the brute force method to find the core set, find all tuples and triples, and
Yeah.
what would be its complex?
Well, if you're looking at all subsets of size d plus 1, it will be n choose d plus 1. But then for each of them, you'd spend linear time to check if they cover the entire set. So it'd be n to the d plus 2. And maybe you could be a bit more clever, but you can't be a lot. You can probably get it back down to n to the d plus 1 with a bit more cleverness because you reuse stuff that you've done before. But you won't be able to say much more. So that's why you have to deal with it. Okay. So as you were saying, right, a random sample doesn't work for a single set. Maybe it might work for clustering. Right? So maybe if you think of your clustering problem as kind of, okay, I have a bunch of different clusters, and I want to find a core set, right? Here's what a reasonable strategy might look like. Sample randomly. I will get a somewhat non-uniform sampling, but I might get a few points here, a few points here, a few points here, a few points here. And that would be enough. If I had a good clustering and I clustered this data, the red points, they would give me the same, roughly the same partition. And again, just like we said before, this works as long as that's okay. No wonder. This works as long as everything is kind of balanced. If all your clusters are roughly balanced. If your clusters are not balanced, if you had, for example, one big cluster with lots and lots of points in it, maybe a few smaller ones, then a lot of your samples would go towards that. And if you're not going to computer K clustering, you might get distracted. So it's not likely to work as well. Right? So let me give you the germ of an idea that is used to, that is sort of built on in more general terms to compute core sets for clustering. And there's a very simple trick at the heart of it that hopefully we can get to. Well, at least we'll start it, and if we can't finish it, we'll continue next time. So let's consider the following idea. So let's look at a very stylized version of this problem. Let's say I have a bunch of points that lie on a grid. Well, no, sorry. I have a bunch of points that lie in the plane, and I put a grid on top of the plane. Okay, so I'm just going to put a grid here. And I'm going to scatter my points everywhere in the plane. Okay. And here's what I'm going to do. In one sense, a core set you can think of as some kind of generalized grid. That you've got a bunch of points. What you're really trying to do is snap them to some small set of points that represent the data. Here, for example, I might say, well, I have a lot of points, but I'm going to build a grid of a certain grid width. And all points within a single grid cell, I'm going to snap to the center. So all the points here, so these points here, they go to this center point here. Right? All these 3 points here go to this center point here, and so on. So you end up with a fixed set of points on a grid. And together capture your data. So my output of this gridding procedure would be only the grid centers with a number that says how many points were associated with that grid center. So I go from a collection of points, n points, to a collection of weighted grid points. And if I built my grid a certain way, I might expect the number of grid cells is very small. So for example, one thing I might do, I might say, okay, let the diameter of the data set be delta, then this width is going to be epsilon times delta. So then I'll need only something like 1 over epsilon cells here. I need 1 over epsilon cells here. And so the total number of grid points is equal to 1 over epsilon squared. Okay? And there are weighted points, but I only need to represent my data by these 1 over epsilon squared points. Right? Of course, in the process of doing so, I incur a certain amount of error. Right? I no longer have exact values for my distances, I have these approximate values. And this can get pretty bad. Right? So the distance between 2 points, imagine one point on this side of the boundary, another point on this side of the boundary. They suddenly get pulled apart. Right? So the error of any movement, right? So, and again, this could be point here to point here. They could be as much as this, as the diagonal of this cell, right? Because this point could move here, and that point could move there. So if you take a point x, and you move it to some grid point x tilde, right? And the distance from x to x tilde is going to be less than or equal to the size of the grid cell. So let's call this g. Oh, sorry. Okay. So there's some error, but you can actually talk about this error. And now I'm just going to cluster the points in the grid with some weighting associated with how many points in the cell. So just like before, I took my data set, I transformed it to some set of small size, and I ran the clustering algorithm, and I pay some error in the process. And so the question is how much error I'm going to pay. So let's see. So you have the original data, and you have its original clustering. And now I have my modified data, and I have my modified clustering. Okay, so when I clustered just the grid points, weighted. And what I want to say is, how much does it cost, whatever cost I'm paying, let's say I'm looking at K median cost. So how much does this cost relate to this cost? I want to get some sense of how good my answer is once I do this. So, of course, if it's looking at K median, we know what this number is. So this cost x prime comma c prime is equal to the sum over all points. Let's capital X. The distance from x tilde to its closest cluster center. Closest x tilde in C. So there's just an unfortunate notation, but that just say the distance to its closest center. Right? That's how we define K median cost. And the same thing for the regular cluster. Notice that these things are important. So let's say instead that we actually assigned the points that we we assign each point here to the point in the clustering that it should have been assigned to. So in other words, x hat was x tilde was assigned to some cluster C tilde, but x tilde came from some x and x was assigned to some cluster C. So in fact, you assign x tilde to some cluster C. Okay. So then you would do something like cost x tilde comma C is equal to the same thing. X tilde 1 to capital X tilde d of x tilde comma closest x tilde of C. Okay. Now we know that this was optimal for x. This was the optimal clustering we got for x. This is suboptimal. So you know that this number is less than this number, right? So we can say that this is x tilde C tilde is less than equal to this point, right? Because this was the optimal clustering of the grid points. This is a suboptimal clustering of the grid points. Okay. And now let's apply triangle inequality. Okay. So what do we know? We know that there are three players in this game. There is x tilde, x, and there's C, and there's x. Right? So we can write the distance from x tilde to any cluster C as equal to, as less than equal to the distance from x tilde to x plus the distance from x to C. X to C. Okay? So if you do that everywhere here, what you end up with is this inequality becomes the sum over all x tilde, distance from x tilde to x, plus the cost of the original clustering. Right? So in other words, once you approximate the data by putting it on a grid, the clustering cost you get can be related to the actual clustering cost plus this extra rounding term, which we'll call R. The rounding term is the amount we pay to round all the data to its nearest cluster set. Right? If, for example, if this number is g square root 2, then this quantity is going to be something like, for this, R would be something like n times g times square root of 2. Okay? Okay. But so what? What does this have to do with anything? What we'd like is that this number is as small as possible. Because we're saying that the cost, the error, right, the difference in cost between the approximation and the true answer is this number R. If you make this number R as small as possible, our approximation is very, very good. And we're working with a much smaller set, which is the big win. So you want to make R small. How do we do that? We want to make R small by choosing a clever way of doing rounding. So notice something here. In this whole argument, I said I'd built a grid structure and I'd done these things very carefully, putting the nearest neighbor on the grid. It doesn't matter. None of those things actually matter. I could choose any collection of points, anywhere, and assign points to their closest neighbor. And this whole argument would still work. This would no longer work, of course. I could no longer say that. But this whole thing would still work. But I'm just measuring the distance from each point to its snapped rounded point. Right, so if I pick arbitrary points and do this, I have some degree of control over what this number R should be. Okay? So what should this number R be? How do I get some bound on this number R? So in some sense, you can think of these rounded points as elements of a coreset. So if you could find elements of a coreset and snap all the points to that, then you would have a coreset. So if I could find a coreset, I would find a coreset, essentially. Which is again the same circular reasoning we were dealing with earlier. Right? So how do we get around this seemingly circular reasoning of that I need a coreset to find a coreset? So here's what we do. To find the core set, we find some very crude clustering. So what we do is we take our points. So let's say we have n points. That's 1 to n. Okay? And you want to cluster them into k clusters. Okay? Instead, what we do is we group them into big chunks. Okay? Into big chunks of points. And what we do there is we cluster each of these groups separately first, in parallel. So we will recursively if you want. So we cluster each of these groups in parallel. Okay? And we get essentially k clusters from each. Okay? And once we have all of these things, we cluster them again. Okay? In a sense, what we're doing is we are using clustering itself to come up with these grid points that we want to come up with. And then we're clustering those centers themselves. The benefit here is that you can do all these things in parallel. So I'm cheating a little bit in terms of the computational model, but you can do these things very quickly. And you don't need to be very careful about this. You need to have a very crude clustering. The crux of the argument, and this is where all of these large-scale clustering algorithms end up working, is that if you take a bunch of data, group them into blobs, cluster the blobs, get these sort of pseudo-cluster centers and cluster them again, the answer you get here is actually a good answer compared to what you want. That these things sort of compose nicely. And in particular, what you can show is that if you do this step here, you get these points and do this. This R that you get, which is basically the internal cluster centers you're getting from this, that this R is less than equal to the cost of the clustering. So what happens at the second level is that you're paying two costs. You're paying R plus the cost of the true clustering. But R itself is less than equal to the cost of clustering. So you end up with a solution that's less than 2 times the cost of the true clustering. And if you're wondering what this has to do with large data computations, the idea is this. That if you can take your data and break it up into small pieces, run some clustering algorithm on each small piece, just like we were saying before, and get some answers, and then put them together as your core set to get a new set of clusters, that answer is going to be reasonable compared to it. And it's not a stretch to say that pretty much every streaming algorithm, or every large data algorithm, not just streaming, for doing clustering, is based on this idea. That if you want to compute a clustering of a bunch of things, break it up, compute a clustering on each piece separately, and then cluster the clusterings. Cluster the cluster centers. And by the way, there's no reason why you have to stop at 2. You can do this over and over again. And next time we'll talk about exactly how that process works. So again, the emphasis here that I want you to take away is not, again, the analysis and the proof, is the design paradigm that it tells you. Namely, to cluster a large collection of points, break them up into small pieces and do local clusterings, and then cluster the cluster centers. That's a very powerful idea that keeps showing up in all these different ways. I mean, it's not the only one, but it's one of the more important ones. So when you have to design your own clustering algorithm, that's what you should be trying to do, even if you can't prove necessarily. So it will work for you. Okay? All right. So I will see you on Thursday. Just remember, next Tuesday there's no class. I'll post a note about this. All right.